Hello and welcome to this presentation of our EuroSys paper, Tesseract. I'm Laurent. This is joint work with Yasmina, Baptiste, Ashvin, and Willie. We're going to talk about graph pattern mining. In short, graph mining aims to find instances of interesting subgraphs, which are called pattern in a graph dataset. Basically, our goal is to enumerate all instances of the pattern within the graph, where each instance of the pattern is called a match. Now, this is an important problem with applications in social networks, chemistry, biology, security, semantic web, and so on. One thing to note is that graph mining is quite different from graph analytics problems like PageRank or connected components. In particular, what's unique about graph mining is the fact that there is significant intermediate data. Even for small graphs with a few million matches, you can actually end up with billions or trillions of matches. Another thing is that graph mining applications are generally more CPU intensive than analytics applications. So here's an example of a graph mining application called graph keyword search. Our goal here is to find all minimal subgraphs connecting a set of labels of interest that are attached to the vertices of the graph. Here we represent the labels using colors. So in this example, you can see on the bottom right that there are 3 matches for the particular pattern in the graph. So generally, graph mining algorithms and systems concern themselves with static graphs. In this paper, however, we're going to talk about graph mining in the different context of evolving graphs. That is, graphs that are updated over time. So our goal is going to be to find the matches in an evolving graph that receives a stream of updates that changes its structure. Specifically, we want to incrementally maintain the set of all matches so that it always reflects the new state of the graph. So designing systems for graph mining with evolving graphs introduces a new set of challenges. First, we need to make sure that the system is correct. That is, it shouldn't miss any matches and shouldn't produce duplicate matches. Second, we need an efficient system that can support thousands to millions of updates per second. And we always want that system to be able to maintain the results in near real time, that is, somewhat interactively. And in particular, that means we can't afford to recompute entirely on the whole graph after each update. Finally, in order to scale out, we need to minimize the amount of synchronization and data exchange across workers. So here's our graph keyword search example again, but this time with an evolving graph. Now you can see what incremental computation means. So on the left, you have the original input graph. On the right, you have the input graph after we applied some updates. So here updates are just adding or deleting edges. And at the bottom, you have the corresponding matches. So our goal is to compute the differences as efficiently as possible between these 2 sets of matches. So here, for example, we have 3 new matches after the update, and we have 2 matches before the update that are no longer valid. So this is the problem that our system, Tesseract, is designed to solve. Tesseract incrementally mines evolving graphs, which is generally thousands of times faster than naive complete computation of the new match set after the updates. Intuitively, this is somewhat expected because updates to the graph have generally a local effect. Like, for example, an update should only affect the vertices in its neighborhood. Tesseract is also a distributed system, meaning it can scale out to a cluster of nodes, and it supports a general programming model. That is, it can match arbitrarily patterns that are defined in code. Interestingly, Tesseract also happens to be faster than static distributed graph mining systems when the goal is to compute the full set of matches on a static graph. Now, there are 2 key ideas in Tesseract. The first key idea is update-based exploration, where we process one update to the graph at a time in isolation and completely independently of other updates. On top of that, we use a differential mining technique to find all the corresponding changes to the match set resulting from this update. The second idea is a series of techniques to avoid exploring duplicate matches. So these 3 techniques are an updated symmetry breaking approach that works for evolving graphs, the use of a separate multiversioned graph store with various versions of the graph corresponding to updates, and an optimization that we call snapshot-based exploration. Now, the result of these techniques is that no data exchange or synchronization is necessary across workers, which allows Tesseract to process updates in a truly task-parallel fashion. So core to Tesseract is this update-based exploration approach. The idea is in fact quite simple. We want to process a single update at a time on a single worker and fully enumerate all subgraphs that include the update in a depth-first search manner. So here, assume that the update is this edge between vertices 1 and 2. The exploration process will start from this update, and it will expand to enumerate all possible subgraphs that include this update. So here we would start by expanding with vertex 3. We would find that this is a match. We would expand with vertex 4. We would realize that this is no longer a match. And we would keep expanding. Here we wouldn't find anything until we backtrack. So then instead of expanding with vertex 3, we would expand with vertex 5 and 7. And we would actually realize that this is also a match. And we would continue doing that until all matches have been found. Now, obviously, the exploration process I described before does not address the problem of actually finding what has changed. This is why we combine it with the change detection technique that will essentially look at an expanded subgraph simultaneously in the graph just before the update and just after the update. This allows the system to figure out whether a match was present before the update, in which case it should be deleted, and whether a match is present in the graph after the update, in which case it should be outputted as a new match. So here in the example, we're going to start the exploration again from the vertices 1 and 2, which correspond to this updated edge. And you can see that as we expand with vertex 3, we're going to find a match in the graph after the update. This is in green here, and we'll output that as a new match. We keep expanding, and we're going to find a match in the graph before the update in red here, and we'll output that as a deleted match. So one challenge with this update-based exploration that I described is it's quite easy to end up with duplicate matches. These are undesirable both from a correctness and from a performance standpoint. So here are two examples of what can happen. The first example is for a single update and is essentially a situation where the exploration order could differ. So you could find the graph on the top left here either as 1, 2, 3, 4 in this order or as 1, 2, 4, 3 in this other order. Same subgraph, but it would be explored twice. It would be outputted twice. Now, a similar issue is also possible when you have two updates. This is here exemplified at the bottom. You could find the match twice, starting from each update. So in order to deal with duplicates in Tesseract, we combine several techniques. The first technique addresses the single update case and is an adaptation of symmetry breaking in the context of evolving graphs. This works by rooting the exploration at the update and then enforcing an order for expansion so you cannot possibly find the same graph with multiple explorations. The second technique addresses the case of multiple updates, and in this technique we leverage our multiversioned graph store to essentially force each exploration to only work within the graph snapshot corresponding to that update. Now this prevents a situation where two explorations from different updates would find the same match. Finally, we also propose an optimization called snapshot-based exploration, where we group multiple updates into a single graph snapshot. This allows us to decrease the overhead of maintaining multiple snapshots and also to speed up mining by skipping intermediate matches between two snapshots. More details about that are in the paper. So how does this work when we have multiple workers? Well, interestingly, it works exactly the same way. There's no need to change anything else. We basically get parallel exploration for free. And this is because each update and its exploration is completely independent of the others thanks to the techniques that I described before. Now, this also means that updates can be processed in any order and that any update can be processed by any worker. In particular, it also means that several workers can process different updates in the same snapshot without having to coordinate. Now to sum up, here is Tesseract's system architecture at a high level. So the system receives a stream of updates that it timestamps in increasing order. Each update is then added into a shared multi-versioned graph store that tracks the state of the input graph over time, and then the update is inserted into a work queue. After that, we have distributed workers that can fetch updates from the work queue and compute the changes to the match set by exploring the graph, just as I described before. Now, an important thing here is that the graph store is not partitioned across workers, but it's kept separately. That means any worker can always read any part of the graph. Finally, the output of the system is simply a stream of changes to the match set that are ordered by timestamp. So a quick word on the programming model. The programming model is actually quite simple. All the programmer needs to do is to specify pattern matching code as they would for a static mining algorithm. In particular, they don't need to worry about the incremental nature of the computation because Tesseract automatically takes care of that. Okay, let's go to the evaluation. So we use 8 commodity servers with standard hardware and configuration in this evaluation. We also use 5 different algorithms: click mining with labels, motif counting, the graph keyword search that I described before, and frequent subgraph mining. We also use 3 different input graphs with varying sizes and characteristics. So first, let me summarize the key results in the paper. The first result is that Tesseract is significantly faster than completely recomputing the matches from scratch. The second result is that Tesseract outperforms the closest system supporting evolving graphs. The third result, which is surprising, is that Tesseract is actually faster than distributed graph mining systems on static graphs. Finally, we also show that we can use Tesseract to track the updates to the match set in a very large graph after we've computed the original match set. So the first result I want to show you is the benefits that are achieved by incremental computation. Here we have the live journal graph on 8 machines, and we compare Tesseract with Fractal. Fractal is a static mining system that is distributed. In this case, we report for 2 algorithms, for click mining and for frequent subgraph mining, how long it takes to process a graph with an additional 0.1, 1, and 10% of updates. In other words, the runtime that is shown here is how long the system takes to compute the updated mining result. Now, Fractal, because it's a static mining system, has to recompute the algorithm from scratch on the entire graph, and obviously that can take a very long time. Tesseract, on the other hand, simply computes the changes, and as you can see, this provides very significant performance benefits. It also shows that if we want to provide any kind of fresh results or interactive graph mining, incremental is the only way to go. So the second result that I would like to show you is how Tesseract's performance compares with Delta Big Join. Now, Delta Big Join is a recent distributed system that supports incremental subgraph queries. The way that it works is it takes a relational approach by expressing patterns as relational queries over the graph edges and then generating matches by joining the edge table. Now, this is not exactly the same as general graph mining like Tesseract, because the system can only look for a fixed pattern, and so you might need to have multiple queries to solve a problem that Tesseract could do in a single pass. However, it's actually the closest system to Tesseract, so this is why we compare with them. So here we report the runtime again on the live journal graph for 4 different algorithms, also using 8 machines. And if the algorithm is such that Delta Big Join would need multiple queries to solve, then we report the runtime of the slowest such query. As you can see, Tesseract performs better than Delta Big Join in all cases. This is due mainly to 2 things. First, Delta Big Join workers need to exchange intermediate candidates at each iteration, which means that there's a multiple of the edge table size that needs to be shuffled across workers several times over the course of the execution. And we measured this to actually be terabytes in some cases. The second reason is that for algorithms that are more selective, such as label clicks or graph keyword search, Tesseract can prune explorations much earlier than Delta Big Join can. So another interesting result is that Tesseract is actually faster than 2 state-of-the-art static distributed graph mining systems. So here we have Arabesque, Fractal, and Tesseract. And we show the time to run 3 different algorithms on the live journal graph, again with 8 machines. And we find that Tesseract significantly outperforms Arabesque and Fractal on static inputs. Now, this is mainly due to the fact that Tesseract workers need not synchronize or exchange any data while mining, and therefore we avoid the shuffle overheads. So finally, the last result that I want to show you is how we can use Tesseract to incrementally maintain the mining result for large graphs. Now, computing the full mining result on these graphs could take days. Of course, it would also take days with Tesseract. However, the cool thing is that Tesseract can actually maintain the result over time once it is computed. So here we're showing the time that it takes for the system to process 1 million updates using 8 machines for the graph keyword search algorithm, and for these two graphs. Now we can clearly see that this is feasible within a few minutes or a couple hours of given 1 million updates to the graph. Now, of course, this was just a preview of the results. There are a lot more results and a lot more details about the experiments in the paper, and you're welcome to check it out if you're interested. So to conclude, I have presented Tesseract, a new incremental graph mining system for evolving graphs. Tesseract provides a general-purpose API. It supports distributed execution in a cluster, and it can mine evolving graphs with millions of updates per second. Now, the key ideas in Tesseract are this update-based exploration approach, which can happen in a totally task-parallel fashion, thanks to the fact that the system makes processing a single update completely independent of other updates, as well as our various duplicate elimination techniques that support this design. It is our hope that Tesseract will enable a new class of interactive graph mining applications to make mining more accessible and intuitive to use in practice. And with this, I'm signing off. Thanks for watching. Bye.